Okay, so in this lecture, we'll talk about the Minkowski's theorem, as said in the previous lecture. And to study the Minkowski's theorem, the thing which we will be needing is the notion of is the notion of volume, the concepts of preserving volume, and the theorem which we proved in the last lecture, that if the natural map from Rn to Tn, if it's not volume preserving, then it cannot be then it cannot be injective whenever we restrict it to some subspace or some subset, whatever. Okay. The main idea of this theorem is quite intuitive to follow. Suppose, let's say I start with R2. Suppose I start with R2, and let's say I have some space. Let's say, let me be very trivial. Okay, suppose this is a large ball which we call as X, let's say, and I consider a smaller ball. Suppose I consider a smaller ball, and now this is quite easy to follow, that if I go by the natural notations, that is, the volume of X is bigger than, suppose I name it Y, is bigger than the volume of Y, right? So in this case, you can easily follow that I cannot squish X into Y, right? I cannot put X inside Y. This cannot be put inside of Y. Okay, clear? In general, I can speak of this in a way that a space X, an arbitrary space X, it cannot be squished into a space whose volume is less than that of X. So the remark or the general idea which the Minkowski's theorem actually deals with is that a space X cannot be squashed into a space whose volume is less than that of X, unless X is allowed to overlap itself. So the X is allowed to overlap itself. What does this typically mean is that if I just suppose I twist X from its half and put both of these halves together, then I might decrease the volume, right? What I'm trying to say is that suppose I take this large ball X, which is sort of like this, and what I do is that, suppose in a way I identify these 2 points, I puncture them together to get some sort of a figure like this, and then what I do is that I overlap this on it, so I might get, yeah, so I'm drawing it like this, but both of these circles follow on the same line. Okay, so I'll get something like this. Okay, and this has far smaller volume than the original X, and this might be put inside here. This might be put inside here. So unless we allow X to overlap itself, I cannot squash it inside any space which has a smaller volume than X. Okay. Yeah. So this is the motivation, one of the ideas to deal with the Minkowski's theorem. In fact, we can say it in some other way, that I can always find a non-zero point of a lattice within a suitable set X, provided that the volume of X is suitably large than the fundamental domain of L. Okay, and this can be this can also be picturized in a very simple way, because if I simply consider R2 again, and I consider a random lattice, I'm not drawing that anymore, but suppose this is the fundamental domain of the lattice, let's say. Okay, so this is the fundamental domain of the lattice, and suppose this is a lattice point, let's say I have this as a lattice point. Okay, clear, it will be like this. And what I'm trying to say is that I choose a set X which has volume considerably large from the volume of the fundamental domain. So suppose I choose X like this, right? So I can always find a lattice point, a non-zero lattice point inside this space X. That's exactly what I mean to say. Okay. And you can easily follow it from here, that this exactly sort of resembles to the previous idea. We'll see that later. But this is the statement which we would be encountering while we state the Minkowski's theorem, and in fact this actually deals with the idea which we presented earlier. But to start with the Minkowski's theorem, there is a simple notion which we require to follow, which is more or less well known, which is called the convex set. So let me just define this simply. So a subset X in Rn is said to be convex if whenever X and Y are in capital X, with, it's better to choose them not to be equal to each other, then all points on the straight line joining them, is also inside X, is also in X. Or we can say that the straight line, this is a certainly sort of a abuse of language, or the straight line is inside X. Okay, or in terms of in mathematical terms, I can say it in this way, that X is convex if whenever X not equals to Y is in X, the point Tx plus 1 minus T Y is in X for all T which ranges from 0 to, okay, clear? So when I say the term inside of X, this typically means that suppose X carries some sort of a shape like this, then this region is called the inside of X. Okay, and this will certainly follows from the way inside the language inside is being used. Okay, and the immediate examples are sort of already understood, I guess. It's all the closed figures you might talk about. Okay, which are closed, for example circles or spheres, ellipse. I shouldn't use the term closed, because we'll see there are closed non-convex sets as well. I should use rather a sort of a symmetrical, no, I won't. Okay, rather let's not talk about these terms, because these lead to confusion, because in fact we'll also see there is a symmetrical figure in which which is not convex. whatever, I guess visually these things are clear, that you can talk about circles, spheres, ellipses, and you can also talk about rectangles. You can talk about triangles, you can talk about rectangles, triangles, in fact polygons, any arbitrary polygons, right? These are all convexes, because you can easily follow it up that whenever you choose a region which is polygonal and you choose two arbitrary points from it, all the points in the line joining those two are still inside the polygon. Okay, so yeah, non-examples, I might say, I might give only one example, say crescent. Crescent. So the crescent is a figure like this. It's a figure like this. Clear? So you can easily follow it up that if I choose a point here and if I choose a point here, then this line, which is the line joining them, this part does not, it's not confined inside the figure. Okay, so this cannot be convex, not convex. Got it? You might also observe that the annulus is not a convex figure. Okay. So now, without further ado, let's get into the Minkowski's theorem now. The Minkowski's theorem. Okay. So we start with a n-dimensional lattice in Rn. Okay. So let L be a n-dimensional lattice in Rn with the fundamental domain as T. With the fundamental domain T, and let X be a bounded symmetric convex subset of Rn if the volume of X is greater than 2 to the power n times the volume of T, then X contains a non-zero point of the lattice, a non-zero point of L. In other words, that the X intersection L is non-zero. It will surely be non-empty. In fact, it will be non-zero. Okay, there is a non-zero point in the intersection. Okay, so this quite resembles the figure which we previously used. So let me just restate whatever I said. So we start with the n-dimensional lattice in Rn, which we call L, and we call the fundamental domain of this lattice to be T, and we take X to be, now these things are to be kept in mind, what we take X to be, we choose X to be bounded symmetric convex subset of Rn. So it carries symmetry, it's bounded and it's convex. So you can think of it just as the ball we started with. If Vx is greater than, that is the volume of X is greater than 2 to the power n times the volume of the fundamental domain, then X will surely contain a non-zero point of L, right? Okay, so now let's start with the proof. Now what do we require it being bounded? I guess now you guys have already understood why we require the concept of boundedness. Why do we require the concept of it being symmetric? We'll see why it needs to be convex when we go on with the proof. But why it needs to be symmetric is that if I have randomness in drawing, if I draw a degenerate shape which is not symmetric, then I can intentionally draw out the space in such a way that I'll avoid every non-zero lattice point. Okay, that's the point to talk about. Okay. That is the reason why it needs to be symmetric. Okay. So now let's start with the proof of the Minkowski's theorem. Proof. The first thing we do is that we double the size of L. We double the size of L to get a lattice. Which we call 2L with fundamental domain with fundamental domain 2T with volume 2 to the power n the volume of T. Now why does it come to be 2 to the power n times the volume of T? If you recall how the volume was defined, so it was defined as the integration of the region. So I have integration over the region T in this case, dx1 dx2 T till dxn. So if I double the lattice, which will in fact double the fundamental domain, so each of the coordinates which comprise the fundamental domain, each of them gets doubled as well. So the 2x1 will in terms of differentials, it will become 2 times dx1, I will get 2 times dx2 and so on and so I get 2 times dxn. So I will have n number of 2's multiplied together. So if I just bring them out, I will get 2 to the power n here, and this part is nothing but the volume of T as usual. Okay, so this is the idea behind it. Okay, so this part is clear. So we get 2 to the power n times the volume of T, and whatever is given in the theorem is that the volume of x, whenever we will start talking about some x, that the volume of that x must be greater than 2 to the power n times the volume of T. So it must be greater than the volume of this doubled fundamental domain. Okay, now consider the torus. We will require all the tools which we have developed so far. Now consider the torus T to the power n, which is r to the power n by 2 to the power l. Okay, so what are we trying to do? We are trying to form the n dimensional torus, where we are not starting with this, we are not quotienting using the standard lattice. In fact, we are quotienting with the doubled lattice. Okay, so then by definition we have the volume of T, let me write it below. Then the volume of T to the power n is same as the volume of 2T. And why is it the volume of 2T? That's also quite obvious to observe. If you recall how we used to define the volume of subsets of the torus, we should define that by bringing that torus back to the fundamental domain, using the bijection of the fundamental domain and the n dimensional torus. And since it's a bijection, it's obviously a surjection. Now since we are calculating the volume of the whole torus, the inverse image of the whole torus is the whole of the fundamental domain. That's why we get the whole of the fundamental domain, the doubled fundamental domain in fact, because we are quotienting with the doubled lattice. So this part is clear, right? Because if you recall, we used to define the volume of x to be the volume of the inverse image of x, where phi from the fundamental domain to T to the power n is a bijection, right? Okay, so let me further add that, and phi inverse of T to the power n is the whole of T, and in this case it's 2T, because we have doubled the lattice and we are dealing with double the fundamental domain. Okay, so we have the volume of T to the power n. I don't mean to say that in that way. The volume of the n dimensional torus is same as the volume of the doubled fundamental domain, but we have seen that the volume of the doubled fundamental domain is nothing but 2 to the power n times the volume of T, right? Okay, so this is something to be kept in mind for now. Now consider again the natural map. There is the quotient map. Consider the natural map gamma as we were doing from Rn to Tn with kernel 2L. I am not writing that anymore. Okay, let me just mention it. Okay, with kernel 2L. Okay. Now this cannot preserve volume. This cannot preserve volume. Why does it cannot preserve volume? So let me just state it. See, observe that gamma of x is contained in t to the power n. This is the now we are starting to using this x. Okay, x as given in the statement of the Minkowski's theorem. X is a certain subspace such that its volume is greater than 2 to the power n times the volume of the fundamental domain. Okay. So now gamma of x is contained in t to the power n, because gamma is just the natural quotient map. I am sending a subset of Rn to Tn. So it's obviously contained in t to the power n. But I know that volume, it's whenever you have two inclusion, then the volume is also under inequality in the same direction. So since, and that's quite intuitive to follow, right? So since gamma of x is contained in t to the power n, so that means the volume of gamma of x, this is less than equals to the volume of the n dimensional torus. But the volume of the n dimensional torus is nothing but 2 to the power n times the volume of t. But by the theorem, by the statement of the Minkowski's theorem, the 2 to the power n times the volume of the fundamental domain, this is less than the volume of x. Okay. Therefore, the volume of the map of x, the image of x, is less than the volume of x. Therefore, this is not volume preserving. Gamma is not volume preserving. But in the previous lecture, we have seen that when gamma is not volume preserving, that is, the natural map is not volume preserving, then it cannot be injective whenever it's restricted to the required subspace. So in this case, it is not injective whenever we restrict it to x, right? Therefore, by the theorem in the previous lecture, gamma restricted to x is not injective. But if gamma restricted to x is not injective, that means that there exists 2 points x1 and x2 from x such that their images under the natural map is same, but they are distinct. Oh, that's something I already said. Okay, but this implies there exists x1 not equals to x2 in x such that their images gamma of x1 is equals to gamma of x2. But gamma of x1, since gamma is the natural map, so gamma of x1 is just x1 plus 2l, gamma of x2 is just x2 plus 2l. So this implies that x1 minus x2 is inside 2l. This follows from the natural properties of a quotient group. Okay, but if x1 minus x2 is inside is inside 2l, what can I say from here? Okay, see, observe that. Yeah, okay, till now let's follow this up. Okay, or rather, let me write it in this way. So which implies 1 by 2 times x1 minus x2 is in L, right? So we have doubled L. Now we are just decreasing the distance x1 distance between x1 and x2 by 2, so it will be contained in the original lattice, right? Because we had doubled the lattice to get that x1 minus x2 is in it. So if we halve x1 minus x2, it will be in the original lattice. Okay, so let it just be 1. We are almost at the verge of ending the proof, but we know that x2 is coming from x, which implies minus x2 is also coming from x, and therefore yeah, we can actually say this by symmetry. Okay, this is the use of symmetry, and by convexity, since x1 is also in x, by convexity, so every point on the line joining x1 and minus x2 will still be in x. So by convexity, every point, let me first elaborate it, every point on t x plus tx1 plus 1 minus t x2, sorry, minus x2 is also in x, right? T is in the range 0 to 1. So let t be is equals to half. This means that half x1 minus half x2 is in x, or this implies that half x1 minus x2 is in x, right? So this is part 2. Good. But since x1 was initially not equals to x2, x1 minus x2 is non-zero, which implies from 1 and 2, this non-zero point, half x1 minus x2, this lies in x intersection. Clear? Okay. So the decisive step of this whole proof was the following, and I'll ask you to try and analyze this out. But I guess if you have understood the proof step by step, then this part is nothing difficult to follow. So the decisive step is that since Tn has a smaller volume than x, it is impossible to squash x into Tn without a overlap. So just try to think about this statement geometrically or visually, and you will get to know what I tried to mean. Okay. So let's end this lecture here. In the next lecture, we'll start with the 2 square and the 4 square theorem. Okay. And for that we will require some extra work to do, but rather these two statements are not at all difficult to talk about. So meet you guys in the next lecture.